Start with electric flux now. This is a short video for only one concept, which is electric flux. But to understand flux, let's first understand its definition. It is number of field lines passing perpendicular to plane surface. Number of field lines passing what? Perpendicular to plane surface. So we have done with the electric field lines the concept where lines of forces, if lines of forces are more, field will be stronger, and if lines of forces are less, field will be less stronger. So here they are saying that the lines of forces has to perpendicular to the plane surface. So for to understand this in detail, we have to think of these two cases. In first case, I'm using two areas, both are equal areas. So in very first area, you see the yellow lines are representing electric lines of forces. So from which exactly two lines are being perpendicular to surface and passing normally to the surface. So by the definition, flux is contributed as 2. But for the same area, lines of forces passing normally to the surface area are greater in number and it is counted as 5. So flux is 5. So if flux increases, matlab number of lines of forces increases, electric field intensity increases. And if electric field intensity increases, flux increases. So in a way, by the first case, we conclude that how do we increase flux? By increasing lines of forces. As lines of forces increases, electric field intensity increases. So in short, we can mention here flux is directly proportional to electric field intensity. In case 2, we are changing now areas. In first area is very small as compared to the previous one. So lines of forces here we can see the two lines are only passing normally to the surface. So flux is calculated as 2. But where in this more number of lines of forces passing normally to the surface, almost 7. So here we can say that as area changes, flux also changes. More the area or larger the area, more number of lines of forces it passes through it. So ultimately, we conclude by the second case, electric flux is directly proportional to area also. So whenever we try and calculate electric flux, we have to count on two factors, which is electric flux intensity, yeah, electric field intensity and area vector. So earlier in 11th standard, we done with the concept of area vector. What is area vector? For any specific area, actually area is not a vector, but when we actually draw normal to any surface or any area, that normal to that surface is known to be area vector. So for this specific area, this normal may be in this direction or in back direction. So that too all are considered to be area vector. Or if I consider this area, so that normal or the area vector may be out of plane of paper or into plane of paper. So area vector is in a way normal drawn to the surface. So if I again look at the areas, whichever we have earlier considered, electric lines of forces, and if we draw area vector, the red line is showing area vector A bar here. It is area vector A bar. And this area vector is somewhere I can say in the direction of electric field intensity. So when I say area vector and electric field intensity both are in same direction, matlab lines of forces are normal, area vector is normal, both are aligned in one single direction. Maximum lines of forces or maximum flux will develop. And in second case also, area vector lies in the direction of electric field intensity and lines of forces are also being perpendicular to the surface. So almost in all four cases, your area vector is in the direction of electric lines of forces and both are perpendicular to the surface of area. But instead, if I incline the surface like this, I'm not keeping area like earlier. So if I want to draw area vector for this case, area vector will be in this direction. But earlier, what we have taken, lines of forces are in this direction. So, can it affect on flux calculation? So the answer is yes. Why? Because area vector is perpendicular and your area or the surface is in this direction. When we actually calculate flux, number of field lines passing perpendicular to plane surface, that we have to count. But your perpendicular vector or area vector is in this direction, and electric lines of forces are going in this direction. So part of electric lines of forces are exactly in perpendicular direction of surface. So how much part or what should be the component of electric field was actually going in the perpendicular direction of a surface or plane surface, that we have to actually calculate for flux. So for to understand this, we have to think of the inclination or angle between area vector or the perpendicular drawn to the plane surface and actual direction of the electric field. Now here you see, if I draw this is what theta. So theta being inclination between electric field and area vector. So if I want to find out component of electric field intensity or perpendicular component of electric field intensity in the direction of area vector, so we have to resolve this vector into two components. And we know if here is the theta inclination between that two vectors, so this must be the direction of horizontal component, and horizontal component can be counted as E cos of theta, and this must be vertical component can be counted as E sine of theta. I hope you understood. As we want to find out flux, and for to flux to calculate, we have to actually find out lines of forces, those are being perpendicular to the surface. Matlab, the lines which are actually in the direction of area vector. But here, your lines of forces are not in the direction of area vector. Lines of forces are inclined with the area vector by inclination theta. So what component of E bar will be in this direction, which is E cos theta. And E sin theta is not in a way contributing to the flux. So whenever your area vector is bit inclined, component of area vector is in the direction of A bar. So for this specific case, how do we calculate phi? Component of electric uh, flux, which is E cos of theta into C. If I want to write this, component of electric flux E cos of theta into area vector A. And if you see, component of E is E cos theta and area vector A. If these two are the vectors A, this A and E are the vectors and inclined by inclination theta given by cosine between it. So this phi can be nothing but E bar dot E bar. Two vectors inclined by inclination theta and given by cosine theta between it. So that this is the definition of dot product. So whenever your area is actually inclined to the electric field intensity, so we have to find out flux by taking dot product for the two vectors, which is E bar dot A bar. So this is how we have to find out. But if we use this logically, this concept, if we use it logically, like here, like if I am taking this area, first area, and area vector for this is perpendicular to specific area, and lines of forces are actually going in the direction of area vector. So both the vectors are being perpendicular to the surface of the area and in one specific direction, one single direction. So in a way, inclination or angle between that two vectors will be 0 degree. And if it is zero, maximum lines of forces are passing perpendicular to this specific area. When this is happening, maximum lines of forces are actually passing through this area, and those are being perpendicular to area. So for this specific case, we are getting maximum field intensity. So if angle between these two vectors is 0, but at what trigonometric function for 0 angle you are getting maximum value? It is what? Cos. So when I do the cos 0, it is 1. So if I actually calculate flux here, it is EA cos 0. It is EA, which is maximum value. So here again, we have used this concept as phi equal to E bar dot A bar is actually proved by using the concept of trigonometry. Now if I say area is kept like this, so area vector will be perpendicular to A in upward direction or in downward direction. Let's say in upward direction I'm taking area vector and lines of forces are going in this direction, horizontal. So we can clearly see that no lines of forces are actually going perpendicular to plane of a surface. So here in this case, we see that E bar is being perpendicular to A bar. And this is the case where we can see not a single line is passing in the direction or perpendicular to the surface. So we are getting minimum flux in this case. So when field and area is inclined at inclination 90 degree, we are getting minimum flux. So again at cos 90, we are getting minimum output, which is 0. So phi can be 0. Again here we can set phi is equal to E bar dot A bar. So in a way, by using the component of E bar in the direction of A bar, you can get phi is equal to E bar dot A bar. Or you can set this equation like this. So total, whenever the electric field intensity or electric lines of forces are not exactly in the direction of area vector, then how do we calculate electric field intensity or electric flux is E bar dot A bar. But this is for regular shapes. If I say your conductor is of irregular shape, so this conductor is somewhere divided into small, infinitely small area elements. So if I would consider this as S1, S2, S3, so there are n number of area elements involved or enclosed by this complete surface area. Again, yellow line indicates the electric field intensity. And for the specific small area S1, we have to simply drop a normal indicating the area vector for that specific element. So if I choose the first S1, this area, and if I drop perpendicular to it, so this is S1 bar, area vector drawn to first element S1 bar. And electric line of force is E1 bar, which is lines of forces passing by this is E1 bar. Again, those are inclined by inclination, kuch theta 1. So flux across this specific area will be simply phi 1 equal to E1 bar dot S1 bar. Now, if I actually calculate for second area, like this is S2, so this area is S2 bar, lines of forces passing by this is E2 bar. So here we can actually calculate phi 2, phi 2 as E2 bar dot S2 bar. Similarly, if I choose third area vector, which is S3, so this is S3 bar in this direction, and E3 bar will be the electric field intensity. So here phi 3 is calculated as E3 bar dot S3 bar. So there are n number of small area elements, and for this total surface area S, we have to find out total flux. And here we can find out that flux by simply, for finite area elements, summation from the limits 1 to total number of area elements are n. So we would use that as EI bar dot SI bar. But if there are infinitely similar small area elements, then instead of taking summation, we would calculate flux as closed loop integration over the surface area S as E bar dot S bar. So here again, you have to find out integration of E bar dot S bar. So when it comes to area vector or when it comes to flux, we have to count area vector and the electric field intensity. So that two are the contributing factors. You got it? So whenever the flux is maximum, when electric field intensity and area both are in same direction and both are normal to the surface, because condition for flux is your lines of forces has to normal or perpendicular to the surface, and area vector is always perpendicular to the surface. So when lines of forces are in the direction of area vector, then only you're gonna get maximum flux. If not, if it is perpendicular, area vector is perpendicular and lines of forces is perpendicular to area vector, or lines of forces are in the direction of plane of surface, so then no lines of forces will cross across the area vector, which means flux is counted, which is zero. And for inclined surface, you have to count on theta. What should be the theta? So flux can be counted as E cos theta into A or E bar dot A bar. So if I want to calculate SI unit of this, SI unit of flux, how do we calculate? Flux is in a way E bar dot A bar. Now we'll substitute SI unit of E bar, which is Newton per coulomb, force per unit charge, and area is meter square. So flux का SI unit is Newton meter square per coulomb. Usually we mention like this. It is Newton meter square per coulomb. When I use 1 Newton meter square per coulomb flux, then that can be counted as 1 Weber. It is what? 1 Weber. Or else you can also mention this flux as electric field intensity is negative gradient of potential. So it is calculated in volt per meter also. Your electric field intensity is also calculated as volt per meter and area is in meter square. So flux ka SI unit, another SI unit is volt meter also. So these two are the standard SI unit for electric flux. And most commonly, flux is counted in Weber. So this is all about electric flux. What we have to remember, like if you're standing, if I consider if this is a window and you're standing here, okay, and wind flow is in this direction. Area vector of window is towards you, yeah, outside the window. So here in this case, direction of wind flow and direction of area vector is exactly 90 degree. So the person who is exactly standing in front of the window cannot feel any kind of wind. But instead of that, if wind is flowing inside the room or wind is flowing in this direction and person is standing here, and this is what the direction of area vector into the plane of paper. So in the direction of area vector, velocity vector works. So the person can feel maximum wind. So this is the case wherein when theta is equal to 90 degree, area vector and velocity vector of wind both are perpendicular to each other. Theta is equal to 90 degree. Output is 0. And when theta is equal to 0 degree, both are in same direction, output is maximum. Somehow same concept is used here. Lines of forces are exactly perpendicular to surface. And we know perpendicular component is area vector. So if both are in same direction, we're gonna get maximum output, maximum flux. And if are perpendicular to each other, we're gonna get minimum flux. And in general, if those are inclined, so it is E bar dot A bar. This is how electric flux can be calculated. Thank you so much.